Okay, welcome to this video lecture about mainly class diagrams, but also a basic introduction to UML and modeling concepts. So we'll talk a little bit about what types of models we can build, why we build them, a little bit about UML. We've already discussed that history a little bit, and how that relates to our programming, and then some of the uses. And we'll get into the concept of class diagrams here. So some of the reasons we might need to know a little bit about UML, certainly from a design standpoint, it's going to be important to us in this class, but also sometimes you may, in the working world, be asked to join an ongoing project, and one of the best ways to find out how things work is to look at the design first. If you have a good concept of how the design works, then you can jump into the code. If you just simply have to look at code, it may be more difficult for you to understand that. We also often may have situations where we have a completed project and we have to kind of reverse engineer it, maybe to replicate it, make it better, maybe to make enhancements to it while still maintaining most of the existing code base, etc. And again, often it's easier to look at the design first and then the code, especially if the code is not well documented, and that does still happen sometimes, even though we'd like for it not to. All these things will help us understand the structure of the code, the behavior of the code, and the function of the code, without necessarily having to reverse engineer the code itself, so that we understand the higher level processes of what's going on. We may even have to go all the way back to the requirements to understand what the purpose of the system is and what the code is doing. So why do we build models? And of course, the purpose of that picture that I just scrolled past is more about architecture than anything else. And one of the reasons we build models is the same reason we build blueprints and things for architecture. We need something to work from when we're going to build the real thing. We need a picture in our heads of how it's going to work and how it's going to look and how the pieces go together, as well as to verify that we've incorporated the appropriate design characteristics, the right kinds of concrete, the right kinds of structures, so that the building doesn't fall down after we put it up, as an example. And the same thing with code. So they help us guide exploration, trying out different things. We can try out different ideas and even discuss with other people our ideas with a model, whether it be about architecture. That's why architects build little scale models and stuff like that. But also in our code, if we have a model first, we can maybe eliminate some of the misconceptions or misunderstandings of the problem, discuss different design ideas with other developers, etc., using a model before we ever have to go to commit to writing it to code. So we can figure out questions to ask, etc., etc. Uncover problems, make sure we've made key decisions properly, etc. So it's a way to check our understanding without the investment in developing the code. And it can help us communicate with other developers, with our clients and users, etc., because we use a lot of pictures, and we've already talked about the fact that a picture is worth way more than 1,000 words. And often we throw the model away when we're done with it. In other words, we don't necessarily always maintain it, although often that's a good idea for large projects because we may have changes in personnel and stuff, and having the models available for them to understand first is beneficial, as we just talked about. So just like a map is an abstraction of the real physical environment, we may use colors to illustrate elevations, urban details, urban densities, people, etc. So we can do a lot of things with maps that don't represent the real thing. We don't have to physically go out and stand in the middle of the street and count people as they walk by. But through census data and stuff, for example, we might have information about population densities. We may draw simple pictures, like this back of the envelope kind of a picture about something. In this case, probably directions somewhere, but sometimes this is basically what we get as far as requirements from a user about what they want a particular software system to do. So we have to be able to start with that and generate something a little more detailed. One of the nice things about models too is it helps us deal with a lot of complexities without having to write code yet again. So the concept of abstraction, in other words, treat objects as the same, ignoring certain differences, ignoring details to see the bigger picture. So we start with very simple versions of entities that are going to be in our environment, and then we add to them as we go. being able to break the problem into smaller pieces and parts. Again, with the model, it's helpful to do that before we start writing code. Being able to project onto different solution spaces, for example, and modularize so that we can maybe reuse some pieces. Maybe we can see from a design perspective some pieces that are part of this particular new system we're building that were also part of an older system, so we can reuse code, reuse objects, reuse concepts, reuse design even from that older environment. This is the same concept as some of the pattern stuff we've been talking about. We've been talking about using things like the transaction pattern. It's an aspect of modularization as well as abstraction. In other words, a lot of problems follow that transaction model, even though they're not in the same problem space. Some may be commerce and e-commerce related, some may be banking, finance related, some may be like your library problem, a resource loan type situation or resource usage type situation, where one resource wants to use another resource for a period of time. All those fit into these categories. So we talked already a little bit about the history of the Unified Modeling Language. We talked about the people, so I'm not going to go through all that again. Remember, it's a notation. It's not a modeling method. It's just simply a way to express our design. And it's promoted by some industry standards and companies as well. There's sort of a standardized meta model, if you will. Think of this as kind of like the set of blueprints that we would use. We're not going to do all of these in this class. You will have a class later where you'll learn more about these. But typically we start, a system would start with use case diagrams. These are diagrams that literally picture the different user interaction scenarios. Kind of like when you go to an ATM, there might be a picture that represents, oh, I'm making a deposit. Another one that represents I'm making a withdrawal. Another one that represents how do I go about making a transfer? How do I go about paying my car payment? Or any of the other things I might be able to do at the ATM. Request a balance and a current statement, all those kinds of things. So use cases are very user-focused and focus on the aspects of the system that do work for the user. Sometimes there are other parts of the system that don't directly have interaction with the user. Like in an ATM, there might be a daily update where it updates the central bank about all the transactions that have happened, and that's not necessarily triggered by a user per se. So we'll have other aspects of the system too, but that's what that particular focus is. Kind of like if we look at a blueprint on the house, we're interested in things like where the doors are, which way they open, and things that are relevant to the people, but not necessarily things that are relevant just to the structure of the house, like the beams and the foundation and stuff like that. Although they certainly are important from the user's perspective, so the house doesn't fall down on them or whatever. They don't directly interact with those pieces. The class diagram, which is one of the ones we are going to do, is a set of diagrams that represent, or a diagram that represents sort of the static structure of the system and the data. What are the things that we need to represent about each element, and what characteristics and operations do we need to perform? And we'll go through each of these in a little more detail here in a minute, so I'm not going to do it here. Okay, so here's what sort of some of the figures that we're going to use to do this modeling. In general, class diagrams look like this with rectangular boxes that have class names and attributes and methods, and then various kinds of connectivity. This is one kind for inheritance. So relationships between them. Use cases show users or things outside the system. These, although they are stick people, they might not actually be physical human beings. They may be other systems, etc. And then functions that occur in terms of interacting or accomplishing the things that these users need to do. Package diagrams we won't be using in this particular one. This is how we sort of put all the pieces together. Think of this as like your separate files and libraries and stuff that we use. State charts is something we're going to be doing. It's a dynamic behavior modeling, how we respond to particular trigger events and stuff like that. Sequence diagrams we won't be doing in this class. These are very useful though for taking basically the classes and the use cases and diagramming out specific scenarios of accomplishing a particular task. So this might be a diagram for a task like make a deposit. And these diagrams are the closest to coding. These are the ones that if we were to turn a design over to a bunch of coders, programmers, that they would use to actually create the code. And some of the tools like rational rows that I mentioned can use to generate a large portion of the code for you if you're using one of those automated tools. Activity diagrams diagram more the business process. They're sort of like the early version of these sequence diagrams where they don't deal with all the specific classes and methods and all that kind of stuff, but we're diagramming an activity. We'll probably do a few of these, although they're not required for your homework assignment, because we can use these for any process. That's the interesting thing about UML. Some pieces are directly related to developing software, but other things like activity diagrams are used by other organizations now that there's a standard to just diagram business processes, things that people are going to do. NASA uses them to replace flowcharts that they used to use to diagram all the different things that could happen in the course of a mission. All kinds of interesting uses. You know, companies like Walmart have used them to create pictures for things like cashiers of what to do when a credit card is declined or whatever. It's basically just showing a set of steps. And we can even show things that could be done in parallel or things where the order in which you do the particular steps doesn't matter, etc. So we'll probably do a couple of these as examples just because they're instructive, but we don't necessarily need them for our assignment. Okay, so classes in UML, as I said, the class itself is represented by this sort of three-part rectangle. The first part is typically the class name. You don't necessarily need the colon. This is meaning a particular instance of a particular class. The first box then shows the attributes that we need, the data, if you will. And this is sort of the first level of class diagram where we're not worried about things like what's the actual variable name, what's the data type. We're just interested in collecting the information. So it's going to be noun phrases, if you will, like date of birth. And this is what I expect you to do for your design assignment and homework 4. And then the other box, which this particular diagram may have filled into, this other box, which is kind of narrow right now but will grow, is where we're going to list the operations or the methods. So like in our rectangle example from a previous lecture, this might be things like compute area or whatever it may be. And then we have different relationships. This particular relationship, this arrow, so all these connecting lines indicate there's some kind of relationship. The type of symbol here indicates what kind of relationship. So this is an inheritance relationship, which we're not going to have any of those in your homework 4 design because we won't have talked about inheritance. We will have them for one of the later homeworks where you're going to incorporate inheritance. And there's ways we can think about these relationships. So an inheritance relationship, as we'll talk more about, is a. So it says an outpatient is a patient. So an outpatient has everything the patient has plus this additional stuff. And the same thing for an inpatient. Another type of relationship indicated by this diamond, and there's two kinds of diamonds. There's unfilled diamonds and filled diamonds. So see, this indicates an aggregation or a partitioning hierarchy. So this means, like, for example, a heart is part of a patient, a kidney is part of a patient, and these numbers indicate how many. So a patient has a collection of 1 heart, 1 to 2 kidneys, 0 to 2 eyes, etc. And they could also, so that's the maximum, and then looking the other way, 0 to 1, 0 to 1, 0 to 1. In other words, there's a particular heart can be associated with only 0 or 1 patient, and 0 because it might be a transplant, so it might be sitting in one of those little ice chests or whatever, so it's not currently associated with a patient. The same with all these other things that can be transplanted. Okay, so we call this an aggregation or a parts hierarchy. And you can think of it just like for a car parts store. What's an engine made up of? Well, there's all these different parts. So when I need to have a whole part hierarchy kind of thing, this is the relationship. Is this open diamond. We'll talk about some of the other ones later. Okay. So here's another example of more detailed one. So this is putting those two diagrams together and labeling all these things. So we call this particular symbol aggregation. This is generalization or also inheritance. This is the box where we list the services or the operations. These are the attributes of the data. This is the class name, and you see the multiplicities here, showing the relationships. And notice here there's another inheritance relationship since all these different things are of type organ. In other words, their base class or their base type is an organ. So a heart is an organ, a kidney is an organ, an eye is an organ. And so organs have certain common characteristics. And what they've done is they've actually sort of done like a factoring, like when you factor out common factors from all of these to create this class. And we'll talk more about that concept later. So a class describes a group of objects with similar characteristics, similar operations, common relationships to others, etc. So you can see here just breaking down that box into what the different parts are. Here's an example of one with some operations in it or some methods, if you will. So you're going to define a bunch of those for your homework assignment. As we move forward toward more detailed design, then the full notation for one of these might look like this. We would have the attribute name, but also its type. Perhaps things like default values, if it has permission issues, like it's read-only or whatever, if it's an array type of or collection type of thing. Notice this looks a lot like C++ or C or C++, but it doesn't have to be. It also has visibility, that's the public-private protected stuff. Operations have names, they have parameters, they have return values, the parameters have types, so like that C colon course means C is a parameter of type course, where course would be a class. So this will be the full notation. And of course, objects are specific instances of the class. So we can diagram those too. We can say Fred Blogs is an employee and has specific values for name, employee number, and department. So this would be an object diagram as opposed to a class diagram. We're not going to do those in this instance, but sometimes it's useful to make pictures of specific scenarios using specific data, because that may reveal problems or other issues with our implementation or our design, if you will. So generalization is another word for inheritance, where subclasses inherit these attributes and methods, and everything about this base class is also part of this derived class, if you will, down here. And again, we're going to talk more about that later on why we need it and how we implement it in C++. So sometimes you'll hear this referred to as a parent class, and these as child classes. Sometimes you hear this referred to as a superclass, as it's done here, which in some cases may be abstract, meaning we don't ever use it by itself. It's always used just as an inner core for these other kinds of things. So if we looked at an actual admin staff in terms of what it contained when we create one, it's going to contain all this data and all these methods, plus, in this case, just this additional method. In this case, some additional data and some additional methods. So there's all of this plus this. So you can think of it as we have a blob, a circle, if you will, that's the staff member, and then we add layers around it to add on additional capabilities. And we'll talk more about that later. Okay, aggregation and composition. These use the same symbol, but they have slightly different meaning. Aggregation is that whole part kind of thing, or something that we're using that's external. The collection, or also called composition, if you will, is, so the aggregation, this open diamond, is when I collect things. So I like to call this collection instead of aggregation. So a car collects or uses several people. In other words, I can have a driver and several passengers, but it's not an integral part of the car, whereas the composition one, which is the filled diamond, is a stronger form of aggregation that implies that if I take this out, then the entity that it's composed of doesn't work anymore, if you will. So, like a car needs an engine, and it's an integral part of the car, whereas the people aren't. Just like the people aren't part of a train, but the train needs a locomotive. Okay, and then of course the multiplicities indicate the number of relationships. Like in this case, it says a particular engine is associated with only one particular car, and a particular car can only have one particular engine. But now on a train, there can be several locomotive engines, so there's a difference there. But a locomotive engine can only be associated either with one train or no trains at a time. I can't have it pushing or pulling two different trains at the same time. So remember, they're slightly different symbols. Okay. So club has members, polygon has to have points, and notice there's also some other keywords we can use here, qualifiers. Like this says the points have to be in order to define a polygon, whereas a circle just needs one point as center, and then it also needs a radius. But as far as using point objects, it only needs one point, whereas a polygon needs three or more. It's a triangle or more. It's a three-sided or more figure. There's no such thing as a two-sided figure, so we've got to have at least three to make it a polygon. Then we can have just general associations between classes. I like to refer to these as users relationships. Like a client may be part of a campaign or start a campaign, but It's not an integral part of the client. It's not a collection or aggregation. It's just a general relationship, just like the relationship between a customer, an order, and a product. So the relationship between the customer and the order of the product is sort of this casual uses relationship as a temporary kind of thing. And like in this example, a campaign may conduct advertisements, and there can be zero or many advertisements associated with a particular ad campaign, for example. But each advertisement is only associated with one campaign. In other words, we're only advertising, Huggies diapers. We're not in the same ad advertising Huggies diapers and, some sort of baby formula product or whatever. So, one thing at a time. And of course, these associations can have multiplicities too, and this just kind of defines what those mean. So we can have optional, 0, ... 1. We can have exactly 1. We can have 0 or more, where the asterisk means many. We can set the lower bound to 1, so there's got to be at least 1. 0 or many is sometimes a slippery slope, if you will. And we can specify a specific range too. It has to be from 2 to 6. So we have a minimum and a maximum, and neither one of which is open-ended, if you will. So that's what those different multiplicities values can look like. You'll also notice that sometimes the associations have names. They're usually verb phrases that help us understand. So we could have a staff member who's the liaison for a client, so the activity here is liaises with. You can have a direction. Without arrowheads, it means that both are aware of each other and their relationship, so the staff member is aware that the client is their designated liaisee, and the client is aware that the particular staff member is their designated liaison. Sometimes it's only one direction, where only basically one of the entities needs to know about the existence or the relationship with the other entity. We can have these multiplicities, we can assign roles to these. All these words help ultimately write the code and help us identify what's going on in the scenario. And here's just some other examples of simple relationships. You can do the arrows like this, or you can also put arrowheads on the lines. The only thing you have to be careful of when you put the arrowheads on the lines is don't make them look like the inheritance arrow. In other words, the one that's a triangle means inheritance. So if we're going to put arrowheads on here, it would just be the angled out 45-degree lines without connecting them together. So that's why some people use the arrows like this for the directions of relationships rather than the other kind. So like in this case, it implies that a campaign conducts an advertisement, but the advertisement doesn't necessarily need to know about the association with a particular campaign. Or a staff member is allocated to a particular grade, like teaching a grade in school, but the grade is not a sentient entity, if you will, so it doesn't need to know about the staff member. Same thing with like playing poker or something. A hand contains a bunch of cards, but the cards don't necessarily know which hand they're in. They're non-sentient beings, if you will. And here's an example of one of the ones that has the arrowheads on it to show the directions, as opposed to the little sort of floating arrows on the line. Okay. We can have bidirectional associations where they both know about each other, if you will. This is really hard to implement like this. We'll talk about some other scenarios later. We can show dependencies, typically with dotted lines, and we can also use dependency types. Anything inside these sort of double angle brackets is often called a stereotype, and we use it to shed additional information. Like this is an interface, which means it's not something we implement directly in these examples. Or this list requires an order and it implements an array list, etc. We can also add comments. We can put constraints on things. We can put constraints in curly brackets like the ordered thing we saw earlier on the polygon. All these are things that we can add to the diagram. So the idea of the class diagram then is to show responsibility, in other words, what operations different objects are responsible for, show subclassing for inheritance and stuff, show navigation, show aggregation and composition, dependencies, etc. So you see with all these different symbols and words on this diagram is very information rich. There's a lot of information there, and most of it is in the diagram. It's in the symbols used and the types of connectors and all that kind of stuff. So once you learn the concept of UML, that diagram could be read by anybody, whether they speak English or not, and understand most of it. And the little bits that are English are descriptive phrases, proper names, stuff like that. So they're not hard to understand or interpret. So we will practice some of these class diagrams in class, doing some for different kinds of examples. But that gives you an introduction and something you can refer to later as you need to review that.